Hi from Tokyo, Japan, and welcome to Jeremy's IT Lab. This video is about the Internet Protocol Suite, often called TCP/IP, the family of protocols that makes communication over the Internet and other networks possible. You've probably heard of some of these protocols: IP, TCP, UDP, HTTP, and so on. If you haven't heard of them, no problem. We'll cover many of these core protocols in this course. From this suite of protocols, we can build what people usually call the TCP/IP model, a way of grouping protocols into layers based on the job they do. In this video, we're going to build that model step by step and use it as a simple map of who does what in a network. This is going to be one of the longest videos in the course, but there actually isn't a lot you have to memorize. We're covering a big picture framework about how networks work. Later, when you learn about things like IP addressing, routing and switching, TCP and UDP, and so on, you'll be able to drop each new topic into this framework and see where it fits and how it works with the others. There's also a lot of history and a bit of argument around different models, like the OSI model and various versions of the TCP/IP model. In this lesson, I'll give you a practical way to think about layers that will help you understand how networks actually operate. As you continue studying, you can add nuance and explore the debates if you're interested, but you don't need to solve those issues today. So relax, don't worry about memorizing every concept, and just focus on the big ideas and relationships between the layers. We'll revisit these concepts many times in later videos. Alright, enough talking, let's get started. Let's begin with the importance of protocols and standards. A protocol is a set of rules defining how data should be communicated between devices over a network. Protocols are the languages that computers use to communicate. Just as someone who only speaks Chinese can't talk with someone who only speaks English, computers that speak different protocols can't exchange data. Since the early days of computer networking, there have been several attempts to define the functions needed for computers to communicate with each other. These protocols were often developed by a specific vendor, such as IBM, to be used with their own products. With this proprietary approach, enabling communications between different vendors' products was difficult, if not impossible. For example, if we have an Apple iMac and an IBM server, each using its own proprietary protocols, the IBM server wouldn't be able to understand a request from the iMac. I'm just using modern devices here as a visual example, but this kind of problem was common in the early days of networking. To solve this issue, today's networks and the devices connected to them use standard vendor-neutral protocols and technologies. A standard is an agreed-upon specification that describes how a protocol or technology should work. When devices follow vendor-neutral standards, devices of all types can communicate with each other. For example, an Apple MacBook can access a website hosted on a Linux web server, and a PC running Windows can send an email that can be read on a smartphone running Android. As long as the devices follow the same standards, they can work together on the network. How did TCP/IP come about? Let's cover a bit of history. Early work on the computer networks that would evolve into today's Internet began in the 1960s, mainly in the US. The U.S. Department of Defense's ARPA, Advanced Research Projects Agency, funded ARPANET. It came online in 1969 to connect mainframes at universities and labs around the country. Here's a map showing ARPANET in the 1970s, connecting locations mostly around the east and west coasts of the country. ARPANET originally used a protocol called NCP, the Network Control Program. There was no TCP/IP in the early days. In 1974, Vint Cerf and Bob Kahn, two of the fathers of the modern Internet, began developing TCP, Transmission Control Program, as an internetworking protocol. TCP went through a few revisions and was later divided into two protocols that are still used today: Transmission Control Protocol, TCP, notice the name change from program to protocol, and Internet Protocol, IP. Together, these two protocols form the foundation of the protocol suite, widely known as TCP/IP today. And the ARPANET fully switched to use TCP/IP on January 1st, 1983. Over time, TCP/IP became dominant over other vendor proprietary solutions at the time, because it was published as a set of open standards that any vendor could implement, and it could run over many different types of networks. And here we are, several decades later, still learning about TCP/IP. That's enough history. Now, who actually defines these standards? Most networking standards are created by independent standards organizations, not by a single vendor. Engineers from many different companies participate in the process. When it comes to networking, there are two organizations you should be aware of. The first one is the IEEE, the Institute of Electrical and Electronics Engineers. I mentioned the IEEE in the previous video when talking about Ethernet cables. The IEEE develops many of the technologies we use on local area networks, such as Ethernet, which is defined in the 802.3 set of standards. The IEEE also develops Wi-Fi, which is defined in the 802.11 standards. These standards include physical specifications like Ethernet cable types, Wi-Fi radio frequency, and how to transmit signals over the physical medium, whether a cable or a radio wave. But they also specify how to format messages to send them to another device over the medium. Both are important topics that we'll cover in this course. The second standards group is the IETF, the Internet Engineering Task Force. The IETF is an open community that defines many of the protocols used on the Internet. A few examples are TCP, IP, UDP, HTTP, and DNS. If you don't know these protocols yet, don't worry, they're all in this course. The IETF publishes its standards in documents called RFCs, requests for comments, all of which are freely available on the Internet. The IEEE and IETF create the standards, and then vendors like Cisco implement them so that devices from different companies can work together. But there are many different standards and protocols, each solving a different part of the overall communication problem. To make sense of them, it helps to group their jobs into layers, making a layered model. So let's look at that layered model. Networks do a lot of different jobs when they move data from one computer to another. Things like the physical transmission of signals, local delivery of messages on a LAN, routing traffic between networks, maintaining end-to-end conversations, and the applications themselves. A model lets us group related jobs into layers. Each layer has a specific role, and each layer uses the services of the layer below and provides services to the layer above. We'll come back to this idea later. Protocols live mostly at one layer. I say mostly because sometimes the lines are blurred and it's hard to categorize a protocol. Some examples of protocols that we'll look at later are IP, TCP, and HTTP. Together, they form a stack of protocols that work as a team, often called the network stack. Here's an example of a protocol stack from RFC 791, which defines IP, the Internet Protocol. It was published in 1981, but this is still the current standard we use today. If you're curious, do a Google search for RFC 791. As I said in the previous slide, RFCs are freely available online, although they can be quite dense reading. You don't need to read them for the CCNA. We can divide this stack into a few layers like this. At the top, we have the application layer, with protocols like Telnet, FTP, and TFTP. I won't define these protocols now, but they're all covered in this course. Then below it, we have the transport layer, with protocols like TCP and UDP. Below that is the internet layer. Here, internet doesn't just mean the internet, the public internet you're probably using to watch this video. It refers to an internetwork, multiple networks connected together. That's the real job of this layer. This is where we find IP, which has two versions in use today, IP version 4 and IP version 6, both important CCNA topics. Finally, we have the link layer, including local network protocols like Ethernet and Wi-Fi. Each of these layers, and the protocols in them, plays a different role in the network. This is the TCP IP model, at least one version of it. The model is a description, not a law. For example, different textbooks and courses use slightly different models, some with 4 layers, some with 5 layers, and some with more. In this course, I'll use a 5-layer model that builds on this one. Before talking about networks specifically, let's use an analogy for this layered approach: sending a letter to a friend via the post. I don't use analogies like this often because they can cause misunderstandings if you take them too seriously, but I think this one is helpful. On the left, you're in your house, and on the right, Bob and his wife are at their house. with a couple of post offices between connected by roads. You write a letter, which is addressed to Bob. You then put the letter in an envelope addressed to Bob's house. Bob's house is a bit far from where you live, so instead of driving directly to his house, you deliver the envelope in your car to Post Office A, like this. Notice the 3 different destinations. Your car is going to Post Office A. The envelope inside your car is going to Bob's house, and the letter inside the envelope is going to Bob himself. Post Office A then moves the envelope to a truck and delivers it to Post Office B, like this. The truck's destination is Post Office B, but the envelope and letter inside keep their original destinations. Then Post Office B moves the envelope to a new truck and delivers it to Bob's house, like this. Once again, this truck has a different destination from the previous truck, Bob's house. The envelope and letter inside still have their original destinations. The envelope is now delivered to Bob's house, opened, and the letter addressed to Bob is read by him. So in this simple mail system, different parts care about different things. The message itself, who should read it, which house it goes to, and how it moves along the route. We can turn those roles into a layered model, and then compare that model to how TCP/IP works. So let's build that model. Don't worry about remembering this model or the names of the layers, it's just an analogy for now. At the top, we have a content layer, the text of the letter, what you actually want to say. I'll call the next layer the recipient layer, the to Bob part, indicating who inside the house should read the letter. Below that is the address layer, which is the destination address of the house where that person lives. Next is the local delivery layer, which handles moving the envelope to the next stop on the path using cars and trucks. From your house to Post Office A, then Post Office B, then Bob's house. With these 4 roles, we already have a simple 4-layer model, similar to the TCP/IP stack I showed before. But we can add one more layer at the bottom. I'll call it the infrastructure layer, the roads and other paths that the vehicles travel on. But really, these bottom 2 layers are related and always work together. If traveling over ground, local delivery uses a car or truck. If traveling in the air, local delivery uses an airplane. If traveling by water, local delivery uses a ship. And often the letter will travel over multiple kinds of paths in its journey. Ground, then air, then ground again, for example. You can either think of these 2 bottom layers as one combined delivery layer, or split them into 2 layers. And that's why some networking models use 4 layers, and some use 5. One of the benefits of a layered system like this is how the layers work together, but remain separate. Each layer has its own job. They work together to deliver the message, but each one focuses on its own task. The content layer focuses on the actual contents of the letter, and that doesn't change throughout the journey. The recipient layer focuses on the individual person who should receive the letter, and also remains the same from start to finish. Likewise, the address layer focuses on the address of the house or building to which the letter should be delivered, and that stays the same as well. The local delivery layer focuses on getting the letter to the next stop in the route, Post Office A, then Post Office B, and finally Bob's house. The infrastructure layer is the system of roads and mail trucks that the delivery process relies on. What happens inside one layer doesn't change the job of the other layers. For example, changing the content of the letter doesn't change the delivery steps, and changing the delivery path doesn't affect the letter itself. When you're writing the letter to Bob, you don't have to think about how the postal service will go about delivering it. Of course, that doesn't mean the layers are entirely independent. For example, if you address the letter to somewhere overseas, that will influence how it's delivered. But that's not your concern as you write the letter. This separation of layers is true in our mail system example here, and it's true of networks as well. Now let's replace letters with data and roads with networks, and build the 5-layer TCP/IP model we'll actually use. Here are the 5 layers of our mail system. Let's map them to the TCP/IP model. The content layer is equivalent to the TCP/IP application layer. The recipient layer maps to the transport layer. The address layer matches the internet layer. These are the same names I showed before for the TCP/IP model, but I'm going to use a different name next. The local delivery layer matches what I'll call the local network layer. This is the layer used for delivering messages within a LAN, a local area network. There are a few different names for this layer, but I'll go with local network. And finally, the infrastructure layer is equivalent to the physical layer. At this point, these names probably don't mean much to you. So next, we'll see how they actually work in a real network between a client and a server. Here is a simple network I'll use to demonstrate. You've seen these icons before. On the left, we have PC1, a client that will send a request to server 1, the server on the right. Between them are two routers, R1 and R2, and two switches. Switch 1 between PC1 and R1, and switch 2 between R2 and server 1. PC1 is running a web client application, in other words, a web browser such as Chrome. Server 1 is running a couple of processes, a web server and a file server. PC1's user wants to access a web page hosted on server 1, so the web client on PC1, let's say it's Chrome, needs to send a request to the web server on server 1. That's the role of the application layer. It includes protocols for communication between application processes and is responsible for creating and interpreting the data. But there's a problem. There are multiple processes running on server 1, a web server process and a file server process, and possibly more. So how can PC1 ensure that its request reaches the correct process on server 1? That's the role of the transport layer. Each process on server 1 has an associated transport port number, 80 for the web server and 21 for the file server. Don't worry about the exact numbers for now, that's for later in the course. The important point is that, to send a message to the web server, PC1 addresses it to port 80. Don't be confused by the name port. These aren't physical ports like we looked at in the previous lecture. Here, a port is just a number used to identify a process running on a host. The role of the transport layer is to provide end-to-end communication between application processes, such as the web browser on PC1 and the web server on server 1, using port numbers. But we still have a problem. Even if the message is addressed to the correct port on server 1, we still have to make sure the message reaches server 1 in the first place. Server 1 has an IP address for that purpose. For example, let's say its IP address is 10.1.1.1. Again, don't worry about the format of the address itself yet. That's a topic for another video. By addressing its message to server 1's IP address, PC1 tells the routers in the path which host the message should be delivered to. That's the role of the internet layer. It provides end-to-end communication between hosts, from the source host to the destination host, using IP addresses and routers. When you think of the internet layer, think IP addresses and routers. And host, by the way, just means a device connected to the network that can send and receive data, such as PC1 and server 1. So we're getting close to achieving our goal of getting PC1's request to server 1, but we're not quite there yet. There are several devices between PC1 and server 1, and we need to make sure the message is properly passed along between them. That's the role of the local network layer. Using protocols at this layer, such as Ethernet, each device sends the message to the next device on the local network. PC1 to R1 via switch 1, R1 forwards the message to R2, and finally, R2 forwards the message to server 1 via switch 2. The local network layer provides hop-to-hop delivery within a local network using MAC addresses and switches. I'll explain the term hop-to-hop more in a bit, and MAC addresses are a topic for another video. Looking at this diagram, you might wonder about the role of the switches. They connect devices in a LAN and pass messages between them. We'll look at how that works in detail in future videos. Okay, and last but not least, we have the physical layer. All of these cables connecting the devices, and the transceivers on the devices that transmit and receive signals. The physical layer sends bits as electrical, optical, or radio signals over the physical medium. Electrical signals over copper UTP cables, optical signals over fiber optic cables, and radio signals over wireless Wi-Fi connections. We've covered the role of each layer, but now let's go from the bottom up, from the physical layer to the application layer, and look at a few more details. The physical layer, also called layer 1, is responsible for sending and receiving bits as electrical, optical, or radio signals over the medium. It defines things like cables, connectors, signal levels, and link speeds, all of the physical aspects of communication. Examples include copper UTP and fiber optic cables, Wi-Fi radios and antennas, and network interface cards, also called NICs. Here are a few examples. UTP ports and a cable on the left, fiber optic in the middle, and an image of a NIC on the right. Each network interface has a NIC like this inside of the device. The physical aspects of transmitting data are very complex, involving a lot of electrical or optical engineering. Fortunately, network engineers typically don't have to know the low-level details of how it all works. So that's the physical layer, layer 1 of our TCP/IP model. In some models, this layer is combined with the next layer, but I think it's useful to differentiate between the physical concerns like these and the logical aspects of layer 2. Next, we have the local network layer, layer 2. This layer provides hop-to-hop delivery of messages on a local network. So what exactly is a hop? A hop is one step along the path between two devices, from one router or host to the next router or host in the path. When PC1 sends a message to server 1, how many hops are there? The first hop is from PC1 to R1. The second hop is from R1 to R2, and the third hop is from R2 to server 1, so 3 hops in total. The switches don't count as hops. A switch just extends the local network, allowing multiple devices to connect. To keep the diagram simple, I only show one host connected to each of the switches, but there could be many more connected like this. The switch allows them all to connect to the same local area network. We'll look at switches and LANs in detail in later videos, so don't worry about them for now. Layer 2 uses MAC, Media Access Control addresses, to identify interfaces. Each device connected to a LAN has a unique MAC address for that specific interface. Since R1 and R2 have multiple interfaces connected to the network, let's add some simple interface labels. G1 for Gigabit Ethernet 1, and G2 for Gigabit Ethernet 2, meaning these interfaces operate at a speed of 1 gigabit per second. PC1 sends the message to the MAC address of R1's G1 interface, its NIC. That's the interface that will receive PC1's message. R1 sends the message to the MAC address of R2's G1 interface. And R2 sends the message to the MAC address of server 1's interface. Once again, we'll cover MAC addresses in another video when we learn about switches. The key protocols at this layer that you should know for the CCNA are Ethernet and Wi-Fi. Others exist, of course, but these are by far the most commonly used layer 2 protocols today. Next up, we have the Internet layer, which is layer 3 of our model. This layer provides end-to-end delivery between hosts across multiple networks. We call it end-to-end because it focuses on getting the message from the source host all the way to the final destination host, instead of worrying about each individual hop in the middle. Remember, Internet means inter-network, between networks. It uses IP addresses to identify hosts in the network, kind of like a home address. In our example, server 1 has the IP address 10.1.1.1. So when PC1 sends a message to server 1, it addresses the message to server 1's IP address. Routers operate mainly at this layer, using the message's destination address to forward the message toward its final destination host. There are a few protocols at this layer that you'll learn about for the CCNA. IP, both version 4 and version 6, and ICMP, the Internet Control Message Protocol. Next is layer 4, the transport layer. This layer provides end-to-end communication between application processes. And why is that needed? Well, in our example, our server, server 1, provides multiple services. It's running a web server and a file server, and perhaps other services. If server 1 receives a message, it needs a way to know which of these services should receive the message. This can also be called process-to-process or service-to-service communication. This layer uses port numbers to identify the processes on each host, such as port 80 for the web server and port 21 for the file server. So when the web client on PC1 wants to send a request to the web server running on server 1, it addresses the message to port 80. And if PC1 wanted to access the file server instead, it would address its message to port 21. The transport layer allows hosts to differentiate between these different streams of data. Layer 4 runs mainly on the communicating hosts, PC1 and server 1. Routers normally operate based on IP, layer 3, not on transport layer information. There are exceptions, of course, but that's a topic for later in the course. Layer 4 is primarily a conversation between the two communicating hosts. There are a few protocols used at this layer. The two most prominent are UDP, User Datagram Protocol, and TCP, Transmission Control Protocol. They both offer some different features, and we'll cover them in this course. Finally, we have Layer 5, the application layer. This is where network communications meet applications. Small side note, this layer is usually called Layer 7. I'll explain why later when we talk about another model, the OSI model. The application layer defines how application processes format, send, and interpret data. So when Chrome on PC1 sends a request to the web server process on server 1, it uses an application layer protocol, such as HTTP, to format and send the message. And that same protocol tells the web server how to interpret the message it receives. Protocols at this layer define message formats and rules for specific tasks. Here are a few examples. For browsing web pages, we use HTTP, or more often its secure version, HTTPS. For file transfers, we can use FTP, TFTP, or another similar protocol. And email uses its own protocols too. Don't worry about the specific protocols or their names at this point. Right now, we're just talking big concepts. Network infrastructure devices like routers and switches typically don't care about application layer details. This is too high level for them. They just move messages across the network. Only the communicating hosts, PC1 and server 1 in this case, actually look at and interpret the application layer data. Now that we've seen what each layer does, how does a single message actually include all of this information at once? Let's see how the layers combine into a stack, and how data moves through them using encapsulation and decapsulation. To show how encapsulation and decapsulation work, let's simplify the network, making it a direct connection between PC1 and server 1. First, the application layer prepares the data to be sent over the network. For example, an HTTP request that Chrome on PC1 sends to a web server running on server 1. As the message moves down the stack, each layer encapsulates the data with a header that contains the information needed by that layer. For example, the source and destination addresses, Layer 4 port numbers, Layer 3 IP addresses, and Layer 2 MAC addresses, among other information. So first, the transport layer encapsulates the data with its header, the Layer 4 header, with source and destination port numbers and other information. Then, the internet layer adds its header with source and destination IP addresses. Then Layer 2 encapsulates the data with both a header and a trailer. The trailer is used by the receiving device to check for transmission errors. We'll look at this in more detail in a later video about Ethernet. Finally, the physical layer transmits the bits as signals over the physical medium, which is an Ethernet cable in this case. I'm showing the message in order from left to right here. So the Layer 2 header is transmitted first, and the Layer 2 trailer is transmitted last. So that was the encapsulation process. Now let's look at decapsulation. The receiving device receives the message as a stream of bits at Layer 1. Layer 1 simply passes those bits up to the next layer. Now it's up to the other layers to interpret those bits. The device examines the information in the Layer 2 header and trailer, and then removes them. This is called decapsulation, or sometimes de-encapsulation. The decapsulation process continues up the stack. So, Layer 3 examines and removes the Layer 3 header. Then, Layer 4 examines and removes the Layer 4 header, and the data is delivered to the application layer. Now the application processes the data, and if needed, generates a response that goes back down the stack and is then transmitted back to PC1. So that's the decapsulation process, which is basically the encapsulation process in reverse. Each device has its own network stack. A message from PC1 goes down its stack, crosses the wire, and then goes up server 1's stack, where the application layer processes it. The response does the same thing in the opposite direction. It goes down server 1's stack, is sent over the wire to PC1, and then goes up PC1's stack, where the data is interpreted by the application. In a real network, there are switches, routers, and other devices between the hosts. That adds more steps to the delivery process, just like the mail system example, where the letter is moved between cars and trucks. But the overall flow is still the same. Each host sends the message down its stack, across the network, and up the other host stack. We'll look at how those intermediate devices, the routers and switches, handle messages in later videos. Now that we've seen how encapsulation and decapsulation work, let's look at what to call these messages. At each stage in the encapsulation and decapsulation process, there is a name given to the message. The combination of data and a layer 4 header is called a segment when using TCP, or a datagram when using UDP. Remember that point. TCP creates segments, and UDP creates datagrams. This difference has to do with how TCP and UDP treat the data, but we don't need those details yet. The combination of a segment or datagram and a layer 3 header is called a packet. Packet is the most common term we use when talking about messages being sent over a network, but strictly speaking, it refers to the message at this stage in the process. Finally, the combination of a packet and a layer 2 header and trailer is called a frame. This is what is actually sent over the wire. You'll never see a packet, segment, or datagram traveling over the wire itself. They are always sent inside a frame. We can also use alternative names to describe the message at each stage, using the term Protocol Data Unit, or PDU. A segment or datagram is a layer 4 PDU, or L4 PDU. A packet is a layer 3 PDU, or L3 PDU. And a frame is a layer 2 PDU, or L2 PDU. Both names are common, so I recommend knowing both. And there's one more important term to learn. The contents of each PDU, that is everything encapsulated by the layer's header and trailer, are called the payload. So at layer 4, a segment or datagram's payload is the application data itself. At layer 3, a packet's payload is a segment or datagram, including the layer 4 header and the data. And at layer 2, a frame's payload is a packet, including the layer 3 and layer 4 headers and the data. Just remember that the payload is what's inside the PDU, not including that layer's header or trailer. Finally, let's talk about how these layers interact with each other. I've replaced the generic layer names with examples of common protocols. Also note the distinction between layer 2 Ethernet, which defines MAC addressing and frames, and Ethernet at the physical layer, which defines the signaling and physical media. Each layer in the stack provides a service to the layer above it and is serviced by the layer below it. This is called adjacent layer interaction. For example, layer 4 provides a service to layer 5 by delivering data to the correct application using port numbers. Layer 3 provides a service to layer 4 by delivering segments and datagrams to the correct destination host using IP addresses. Layer 2 provides a service to layer 3 by delivering packets to the next hop using MAC addresses. And layer 1 provides a service to layer 2 by sending and receiving the frame's bits as electrical, optical, or radio signals over the physical medium. Each layer relies on the layer below it to do its job. There's also a related concept. Each layer communicates with the same layer on other devices, and this is called same-layer interaction. For example, the application layer on one host sends data to the application layer on the other host. A segment or datagram is addressed to the layer 4 port number of the correct application on the destination host. A packet is addressed to the layer 3 IP address of the destination host. A frame is addressed to the layer 2 MAC address of the next hop. And signals sent out of a physical port are received by a physical port on the connected device. This layered cooperation, within each device and between devices, is what makes network communication possible. Just like in our mail system example, the separation of layers is key to how networks work. Each layer has its own job and provides a specific service to the layers above. Because the layers are modular, we can swap protocols at one layer without changing the others. For example, instead of a web page exchange using HTTP and TCP, maybe it's a file exchange using TFTP, Trivial File Transfer Protocol, over UDP. The lower layers in the stack can use IP and Ethernet without worrying about the details of what the upper layers are doing. And if instead of a wired Ethernet connection, it's a wireless Wi-Fi connection, layers 1 and 2 can change to Wi-Fi without affecting the upper layers. As long as each layer keeps its contract with the layers above and below, we can improve or replace protocols at different layers without redesigning everything. That flexibility is one of the main benefits of a layered model. Now that we've built this 5-layer TCP/IP model, let's see how it compares to other models you'll see in other courses and books, like the OSI model. You might have heard of the OSI model before. If you've studied IT before, you almost certainly have. As I said at the beginning of this video, TCP/IP development started in the 1970s with work on ARPANET and the early TCP/IP specifications. But in the late 1970s and 1980s, the International Organization for Standardization, the ISO, designed a 7-layer model called OSI, Open Systems Interconnection, and a matching protocol suite. The goal was to create international vendor-neutral networking standards that could unify existing proprietary stacks and potentially replace TCP/IP as the vendor-neutral choice. Here is that model, with 7 layers from top to bottom: application, presentation, session, transport, network, data link, and physical. Governments, including the US, promoted OSI as the preferred or recommended stack for new deployments. And for a while, many people thought OSI was the future. But OSI protocols ended up being developed too late and were too complex, and they never gained the same level of deployment as TCP/IP. I wasn't around at the time, but my understanding is that this was largely due to the bureaucratic nature of the approach to developing OSI and its protocol stack. The process was very top-down. Committees designed the protocols in detail, and vendors were expected to implement them exactly as specified. TCP/IP used a more bottom-up approach. In the end, TCP/IP won in the real world, although some OSI technologies are still used. Today, almost all networks use the TCP/IP protocol stack, but the 7-layer OSI model survives as a reference and teaching model, and as a common way to talk about layers. Actually, most networking resources use a 5-layer model, like the one I covered in this video, but with names borrowed from the OSI model. Here is that 5-layer model. I foreshadowed this earlier in the video, but this is why the TCP/IP application layer is often called Layer 7, because the application layer is Layer 7 of the OSI model. I've also highlighted the 2 layer names that are different from the model I introduced. Layer 3 is called the network layer, and Layer 2 is called the data link layer. And to make things even more confusing, here's a selection from Wikipedia of different models proposed by various authors. Here we have the 4-layer TCP/IP model I showed at the beginning of this video. Here is the 7-layer OSI model, and the adapted 5-layer model I just showed in the previous slide. When you see all of these variations, you might wonder which model and which names you should actually learn. Of course, I recommend the 5-layer model I presented in this video, because I think its names best match the job of each layer. But this 5-layer model shown here is probably the most common in books and other resources. The only differences from my model are that Layer 3 is called the network layer, and Layer 2 is called the data link layer. In the end, it's not that important. In practice, people usually just refer to Layer 2 and Layer 3, and you won't be quizzed about layer names on the CCNA exam. Before wrapping up, let's review the key concepts from this video. I won't explain everything again here, I'll just point out what you should focus on as you review. The first is, of course, the TCP/IP model itself. You should know the general purpose of each of these layers. I also recommend knowing these more commonly used names borrowed from the OSI model. It's also important to understand the encapsulation and decapsulation processes. In encapsulation, the sending host adds headers and a trailer to the data to prepare it for transmission over the physical medium. In decapsulation, the receiving host removes the headers and trailer layer by layer until it gets to the data inside. You should also know the names of the different PDUs, Protocol Data Units. The Layer 4 PDU is a segment when using TCP and a datagram when using UDP. The Layer 3 PDU is called a packet, and the Layer 2 PDU is called a frame. The frame is what is actually transmitted over the physical medium. And finally, you should understand adjacent layer interaction and same layer interaction. These concepts describe how the different layers work together within each host and with their counterparts on other devices to achieve communication between applications over a network. That's all for this video on the TCP/IP model. By now, you should have a mental picture of the 5 layers, what each one is responsible for, and how they work together using encapsulation and decapsulation. You don't need to remember every example or historical detail. The important thing is that you know the layers, their general roles, and the idea of PDUs and layer interaction. We'll keep coming back to this model throughout the course. You'll hear the terms Layer 1, Layer 2, Layer 3, and so on many times. As we dive into topics like Ethernet, IP addressing, TCP, and routing, you'll be able to place each new concept at the right layer and see how it fits into the bigger picture. Just remember, this is a model, not a law. Real protocols don't always fit neatly into a single layer, and that's okay. The model is just a tool to help you think about what's happening in the network. If you'd like a structured companion to these videos, I've also written 2 books, Acing the CCNA Exam, Volume 1 and Volume 2. They go into more detail than I can fit in the videos and include hundreds of diagrams and practice questions. I honestly think they're my best work when it comes to teaching the CCNA. If you're interested, you can find them on Amazon or use the links in the description to get them directly from the publisher. Thanks for watching. Before we wrap up, I want to say a quick thank you to the channel members whose names you see on screen. Your monthly support helps me keep making these videos and keep this content free for everyone on YouTube. I really appreciate it. Thank you for your support. If the video was helpful and you want to support me, click the join button under the video. Thanks again.